Good morning, friends. I welcome you all here in my course, Engineering Thermodynamics. I am in module number 1, and in this module, I have covered some 6 to 7 lectures and discussing about the pure substances, their properties. We have seen that how the pressure, volume and temperature, these are the properties which are the point based properties. They are not depend upon the path. So for this property we can get the exact differential. There are some other phenomena like work and heat, which is my today's topic. They are not depend upon they are depend on the path, and so their value will change how this process is moving. So today my topic is work and the heat, and I will be discussing in this topic how the work is produced and how these things are done. So I will be covering these topics on the day, that is the thermodynamic work definition, simple compressible substances and equilibrium, work in isothermal and polytropic processes, other forms of work, work done in expansion and compression of a system. Then I will go, last topic is heat and some facts about the heat. This I am going to discuss and hope this will be very useful. As you know that I am in the thermodynamic, and this word thermodynamics comes from the thermic. This thermi means heat or the temperature, and dynamics means power. So the classical definition of thermodynamic is to give or to produce work or to produce a power by giving some heat. So today's my topic is on that, how work can be obtained from the heat. And today I am just discussing the basic concept of work and the heat and how this work is very important. The concept of thermodynamic came by the generating of the work. How we can reduce the workload of a human being. How a human can be comfortable by using some thermal properties. That's why the steam engine was first developed in 17th century. After that, lot of heat engines, SI engine, CI engine, 2-stroke engine, 4-stroke engine, now gas turbine engines. These engines are used for the propulsion of the vehicle, for moving or giving the thrust to the vehicle so that it is moving very easily. Thermodynamics involve not only in mechanical or aeronautical but in all other field of engineering. Everywhere thermodynamics is applicable. Not only this, even for the data transfer, information transfer, everywhere thermodynamics is applied. It doesn't mean wherever this heat is flowing, then only you can use the thermodynamics. If heat is also not there, you can use for the transfer of the information, how these informations are disturbed. So this part is as entropy. Entropy I will be discussing, I think, in after some hours. So, but it is also applicable there. So I will go today with some thermodynamic work, that is the definition, and this you can see that very, very important and very classical definition, and that we have to see that work is done by a system if the sole effect on the surrounding could be that of raising a weight. Here we have to understand very well that it is very, very classical definition of the work. So work is done by a system if the sole effect, this we have to find out the keywords. Here the sole effect on the surrounding could be that of raising a weight. Very, very important. We should understand, then only we can apply the knowledge of work on our, and it is a could be, not 100%. So just I want to tell that work is done by a system if the sole effect, the total effect on the surrounding could be that of raising a weight. So suppose this is your system. In this system, this line is your boundary of the system, and here we have to operate and get some work done. And here if we put some rope like this, and here I am putting some weight here. So if this system is able to rotate this shaft, this is the shaft here, and by the rotation of this shaft, it is going upward, means it is working against to the gravity. And what is the gravity here? Gravity is a resistance. It is opposing motion. There is a difference between the applied force and the resistance force. Here, if I am able to lift the weight by the work, thermodynamic work, or the system is able to make some work, and this work is able to lift the weight against the gravity, then only we will say that it is a thermodynamic work. But if you see in the physics or in our normal work, we are not concerned with resisting force. We are W is equal to F into delta X, where F is an applied force. Suppose this is the one object and I am pushing like this. So it will go from here to here. I am applying a force. My force is making this to move. This is a physical work, not a thermodynamic work, because this should move with some resistance. This should also apply. So a resistance. So this same thing if I am dragging on my sand. Same thing, by the same application, I am dragging on the sand. Sand will give more friction. I need more force to apply. That force, which force is resisting the motion of the object which is moving, that force we need here in thermodynamics to use to calculate the work. So if resisting force is not there, let it be motion. I will explain this thing in this example only, that how this, if it is moving also, there will not be any work as per the thermodynamic concern. So here work is done by a system if sole effect on the surrounding could be that of raising of a weight. So here the raising of a weight doesn't mean that you just lift the weight. The raising of the weight means it is a resistive force. You should able to work if you are your system is able to make against to the some resistance, then only your work is done. And this application should be in surrounding. Your system should generate the work, and this work has to be transferred to the surrounding. Then only we can say that there is a work. And if this is not happening, this is not the work. If it is moving by its own towards the gravity, towards the earth, this weight is not considered as a work. But as per the physics or the physical work, a simple work, the work is done because it is going towards the moving. Delta X is there. Force is also there. Gravitational force. Force into X. It will be work. But for the thermodynamics, this work is not considered. The work which is able to resistance, the force which is able to stop, that is the force which we can take for the thermodynamic operation. So for thermodynamic work, this W is equal to resistance force into displacement. So this resistance force I can write here as F resistance into delta X. So this is the W. So that we have to ensure that we should understand that there should be resistive force. I am going to example here that no work, okay, just free expansion or unrestricted expansion. Work is zero as no resistance force is available. No resistance force is available. So how we can see here? Just you can see there is a, here this is the body and here is the system. This is the system here. I am just putting this thing. This is the system. This is the system here, and there is a valve here, this valve, and here is a vacuum. This is the here. This is the vacuum here, means there is no resistance in this chamber. And there is a valve. If I rupture this valve from here, and here is some pressure is here, this will expand here. But as there is no resistance, there will not be any work. But if you see the normal physics, other than thermodynamics, here also force is there, and the displacement from here to here is moving. Your expansion, the volume is increased. It is a V1. Now this is the V2. So V2 minus V1, this much into pressure P. P into V2 minus V1, work is done. But in the real sense, there is no work because there is no resistance, because this system is put as a vacuum, and vacuum do not have any resistance. This type of case is called the no work case, or it is a free expansion or unrestricted expansion. In the future problems, if any problem is given that it is in vacuum, it is free expansion or unrestricted expansion, immediately you can say that it is a zero work. dW is equal to 0. No work. Work is 0, but there is a no resistance. Work done due to displacement of moving boundary for a simple compressible substance undergoing a quasi equilibrium process. So in the next slide, I am going to discuss about the work done due to displacement of moving boundaries for a simple compressible substance. So we have to first understand what is the simple compressible substance under the given a quasi equilibrium process. These two things we have to understand, because in thermodynamics your every problem is in equilibrium condition, and all the substances mostly we consider that it is a simple compressible substance. So if this is like this, so we have to understand what is a simple compressible substance. First, very much essential, every student has to understand that what is the simple compressible substance, and also what is the quasi equilibrium process. If we understand these two things, then only we can apply the thermodynamics principles and equations, because all these equations are derived in these two conditions. So we have to see that how it is happening. So I will discuss here first simple compressible substance and equilibrium. So simple compressible substance, where only pressure, volume and temperature are significant, those cases we can deal as a simple compressible substances. There is no electrical, there is no magnetic, these things are not considered. No surface tension, no other type of forces are not considered. Only their thermodynamic properties like PVT and related to this PVT like enthalpy, entropy, these things are only considered. Those substances are called the simple compressible substance. So we should make sure that the process or the material or the substances which we use, they only follow PVT. They are not influenced by the electrical force, magnetic forces, or some other gravitational or some other forces we are not considering. So like this, most of our cases and all things which we are going to derive in the future classes, they all are depend upon this simple equilibrium substances. Now we have to discuss about quasi equilibrium process. If you see here that we have one, this is the cylinder and this is the piston here. Here we have the cylinder and here we have the piston, and this is the system here. System may be any substance like air, water, nitrogen, anything. Here we have the, and this is the piston, and you see here we have put some weight. This is the weight. Maybe assume it is a 1 kg. This 1 kg weight, here is the weight. I am just giving a explanation of the quasi equilibrium condition. This 1 kg of weight is sliced so many weights, 100 or 200 or 1000 slices, small slices like this, and they are put on top of this piston. Now the system is here. I will remove this one. If you see here, if I remove this one, first one, very infinitesimal small amount of weight, maybe 1 gram. Out of 1000 gram, I have removed the 1 gram. So what will happen? Inside this, very slow motion, it will go upward because weight is reducing, and inside everything will be in the same condition. Your pressure, your volume and the temperature all will remain same in all the points, because this process is very slow. That type of situation, and slowly if I remove 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like this 1000 pieces, I am slowly I am removing. Your whole system will be in quasi equilibrium condition, and this type of processes are called the quasi equilibrium process. Most of our discussion will be on quasi equilibrium process, because in this condition the resisting force is equal to the applicable force. Application force means the force which is acting from the bottom will be equal to the force acting on the top. So this is the equilibrium, means your state of this thing is in equilibrium. So that is why it is called the quasi equilibrium process. Now, work done by the system. This we have to understand, and we should see that how the work can be done. So here I am showing the two things here. First is the isothermal process, and the second is the polytropic process. So in isothermal process, we can see that PV is equal to constant. PV is equal to constant. So here work done, always del W. We should not write dW. It is the exact differential, but del W is inexact. We should be very much sure that we should understand what is the difference between dW and the del W. Del W indicates that it is inexact. The differential is not. It is a partial derivative. Partial difference is required. This will not give the correct point value, and this is having the path value. It depends upon the path. But this dW depends upon the point. So if you see the properties like pressure, volume and temperature, they are the dP we can write, dV we can write, dt we can write, but we cannot write for work and for the heat Q. We cannot write like this. It is not correct. We have to write del Q because it is inexact differential and it is depend upon the path. They are the path functions and they are the point functions. All properties are the point function. These properties are depend upon point to point. But this work and the heat, they are not depend upon the path. Their work and heat, they are depend upon the path. So they are not exactly from 1 to 2. There may be different path. So this I will be discussing in so here I am going to derive the work by the if the process is isothermal process. So work done del W is equal to W12 differential from 1 to 2 P dV. This we have seen in our pressure into volume. So here 1 to 2 we can write for the pressure, we can write from here P is equal to C by V. So this C by V, in place of P I am putting C by V into dV. Now C by V, it is dV by V. If you take the integration of dV by V, we will get ln V2 by V1. ln V2, C ln V2 by V1. So for this C, we can write P1 V1 is equal to P2 V2 is equal to C. So in place of C, I have put here P1 V1 log n V2 by V1. So the work done during the isothermal process, we can summarize that work done is equal to P1 V1 log V2 by V1. So this is our first equation in which we can calculate the work done by a system. If this system, so we should know the P1, V1 and V2. Three quantities, if we know, we can find out the work done by the system. It means if you know the pressure and how much volume it is shifted, how much change in the volume V2 and the V1, if you know very well, we can calculate the work done by the system. The second case, which is the universal case, where it is called the polytropic process. So PV is equal to N is equal to C. PV to the power N is equal to C, where N should be, should not be, okay. N should not be equal to 1, okay. So N should not be equal to 1. If it is N is equal to 1, it is again the PV is equal to C, like this case. So this case we have already studied. So PV to the power C. So N should not be equal to 1. So here also if you see, this del W is equal to W 1 to 2 integration 1 to 2 CV. Here we can see here that PV, PdV, P is equal to how much here? So here we know that W12 is equal to integration 1 to 2 PdV. But here P is equal to how much? C by V to the power N or C V to the power minus N. This C V to the power minus N I have clipped here. C V to the power minus 1 into dV. Now this C is a constant. V to the power minus 1. So we have to integrate V to the power minus 1 plus 1. 1 to 2 divided by 1 minus N. So we got here C V to the power 1 minus N minus V1 to the power 1 minus N divided by 1 minus N. Now for this C, we have to make that from here. P1 V1 to the power gamma N is equal to P2 V to the power N. So for here, we can put here that P1, first case, this C is equal to, we can make P1 V1 to power N. So this, if you put here P1 V1 to power N or P2 V2 power N. So here this N will be cancelled and here also N will be cancelled. So P2 V2 minus P1 V1 divided by 1 minus N, where N is the process which is not equal to the 1. That is the condition. If you put the 1, work will be 0. So this is except the case 1. If it is a constant volume, if you see, if it is a constant volume, so here V2 minus V1 is equal to 0, this whole will be again 0. So this is the process which we have to understand. This equation number 2 and 1, they give the value for the our work done by the system. So now I will go for the next issue, some other forms of the work. So we have done the simple PDV work, isothermal or thermodynamic work, isothermal, polytropic, constant, isobaric, isochoric, all the things we can find out by this previous equation. But we have some other form of work, like a soft work. So if this is the soft here, this soft is rotating with omega velocity, and there is a torque. There is a torque. This torque into, so what will be the work done? The rate of work done per unit time is equal to torque into omega. This is the rotational velocity per unit time. So this is work per unit time is called the power. So this power is equal to torque into rotational velocity omega. So this is a soft work, mechanical work. Now if you see the flow work, okay, this you can see here that if you see here that this is a pipe here. Here full, it is full of water, assume. This is here one. The strip is here. So this is from 1, 1. It has moved to 2 and 2. Next point, 2 and 2. This first layer has to move from here to here. To moving from here to here, this side we need some additional force. Then only it will be moving. Okay, so here pressure of the water is P, and the area of from here to here, the cross-sectional area, here I am just showing here. This is the cross-sectional area. This is area is A. So here how much force is applied here? It is P into A. This is the force. And how much distance is traveled? From 1 to 2 is a delta X. So how much is the, this is the work done. So work done is how much? PA into delta X for per unit mass. So M is equal to what? M is equal to density into volume. Density into area into dx. So we can see that per unit mass, how much work is there? PA dx by rho A dx. A dx is cancelled. So here you will get P by rho. So work done per unit mass is equal to P by rho. And we know that rho is equal to inverse of the specific volume. So here 1 by rho is equal to V. So here we got the flow work is equal to pressure into specific volume. Per unit mass of the work done is equal to pressure into specific volume. Very important, because this will be used in our future solution of the problem. Now the next type of work is work done due to the stretching of a, it is happening due to the surface tension. Surface tension. If you see here that this is a rope, you are putting here some load here. This is the wire here, and you are pulling like this in this direction. So what will happen? There will be the length of this wire will increase first. Increasing in this direction, this length will increase some delta x, and force is here. So this force, because it is resisting force here also, so this force or resisting force into dx is equal to work done, and this type of work done is called the stretching work done. Work done due to the stretching, and this is happening due to the surface tension. You are pulling this string like this, so the surface will extend. This extension will give the work, and this is called the work done due to the stretching. These works which I am handling here, we are not considering in thermodynamics, but these works are also, we should understand that this type of work, that is why it is a simple compressible substance. If any of these works are taking part, we cannot assume as a simple compressible substance. Next is the electrical work. So if there is a E is the electrical potential or EMF, so this work done is equal to EMF into dq, where q is the charge. So if like this, it is called the electrical work done. Next is the magnetic work done. How the magnetic work is done? If there are some ions in paramagnetic salt, and if you put the high power magnetic field, the particles of ions will start moving from one side to another side, and they will form a very organized system. Their orientation will change from initial. This type of work is called the magnetic work. So this, or if we are adding this thing in our activities, then we cannot say that it is a simple compressible sentence substances. For the simple compressible sentence substances only, we are following the equations. So now sign convention for the work. So work done by the system. Work done by the system. This is the system. This is the system. This is the surrounding here. This is the boundary of the system. And if this system is giving work to surrounding, then this work is called the plus. It is a positive work. Then it is a positive work. And if the work is given by some external agency, by the surrounding, then this type of work is called the negative work. It is called the negative work. So this is a convention which we will be following in our whole this course. So understand that if the system is giving the work to surrounding, it is a positive, and if system is taking from the surrounding, then it is a negative. So for all our case today onwards, whatever cases we are handling, this everywhere we will use the same sign convention. You can change it also, but everywhere you have to change accordingly. Next, I will discuss about heat. So what is the heat? So we have discussed about the work. Now we should also something discuss about the heat. So what is the heat? Heat is an energy in transient due to temperature difference. So heat is always will be in transient. If you put a bucket of water, a bucket of hot water, and you can say that this bucket has got a lot of heat. This is not a correct statement. Heat cannot be possessed by any system. Heat will always be in the transient. It will always move. So heat is an energy, and this is heat is an energy in transient. It means the energy when it is moving due to temperature difference. And if there is a temperature from high to low temperature, heat will always move. So this is the definition of a heat, that heat is an energy in transient due to temperature difference. So surrounding is greater temperature. If you see here, this is the surrounding, and if it is the 100 degrees centigrade, and here is a 20 degree centigrade, heat will go from surrounding to system. And if you see here that if the surrounding is 10 degree centigrade, if the surrounding is 10 degree centigrade, then and it is 20, so heat will go from here to here. This is the Q. So if, and this is the positive Q and this is the negative Q. So if the heat is going to the system, it is a positive, and if it is heat is coming from the system, it is a negative. Always it will move from high temperature to low temperature, and heat given to the system is a positive and it is coming out of the system is negative. This convention we should understand, we should always keep in mind. And if you just, I want to show here, if it is work, it is a positive, and if this is the work is a negative. So work going is negative, coming out is positive, heat coming in is positive, going out is negative. This we have to take care of. Now what is the similarity between work and the heat? This also we should understand. So both are energy intransient. Both means heat and work. Both are energy intransient. They are moving. The system does not possess any heat. Always, no system will have any heat or work. Both will not have. They all, work will be also moving either in or out. Same way, heat will also move from out or in to out. So that is the first similarity, that both are in transient. Both are energy, but both are in the transient. The differential of both are in inexact differential. Not the inexact means it is like this or it is like this. Del will be there, not D. So differential of both are in inexact differential. So here del Q and del W depends upon the path, not on the point. Work out is positive, heat in is positive. This we have to take convention in a nice way. Take convention in a nice way. That we have to take care of. So now I will discuss about, again just I will give some important point on the work in thermodynamics process. So energy can be transferred to a system by heat or work. So just now I have given very much clear. I am just summarizing this work which I have done, that energy can be transferred to a system by a heat or the work. The system will be a volume of a gas always in equilibrium. So the system will be always inside the chamber, maybe air or gas or anything, and this will be always in the equilibrium. Consider a cylinder with a moving piston. I will show you. A piston is pressed a distance delta y. Work is done on the system during the volume. So a piston, if it is compressed, then work is done on the system. Means it is a negative work. This you can see here that in this there is a piston here, there is a pressure and the volume. The volume is high here, and from here we have shifted this piston here. The volume is reduced now. From here it was here. If you see here, it is nearly here. This much you have gone down. So this volume is reduced. So the pressure is positive. This work is positive or negative? The work is negative because work is given in this. You see here the arrow. We are pressing this shaft and then it is compressed. So this work will be negative because the volume is V2 is less than V1. So W is equal to P V2 minus V1. So if it is less, the W will be negative. So this we have to take care of, that a gas in a cylinder occupies a volume V at a pressure P. B is the pushing the piston down, compresses the gas, and this compression gives the negative work, means work is done on the system, and this may be by the motor is pressing the piston. Now we will see that further aage. Work done compressing a system is defined to be positive. So work done compressing a system defined to be a positive. Since delta V is negative, a smaller final volume, that is A into delta Y is equal to V. So this W is equal to minus P into delta V. This you can see that W is equal to minus P into delta V. Gas compressed, so work on gas is positive. Work on the gas is positive. Gas expands. Work on gas is negative. This you can see here in the same case. The pressure is P0 and it is V1. It is expanding to V2 cross section. Work done by the expanding gas. So work done is done by the gas if it is expanding. So this is done by the, and this is the positive. Can only be used if gas is under constant pressure. This type of systems for a constant pressure, we can use an isobaric process where pressure is constant, that is P1 is equal to P2. Represents on a pressure versus volume graph a PV diagram. Area under any curve is equal to work done on the gas. If the volume decreases, work is positive, work is done on the system. If the work is done on the system, this you can see here that here is the pressure P0, it is isobaric process here. From here to here, 1 to V2 it is increasing. So this area which is shown here, this area will be giving work is equal to P0 into Vf minus Vi. This is the work done by a constant pressure process, in which this you can see here that a PV plot representing the constant pressure process shown in the figure. The area of the shaded region, that is PO Vf minus Vi, is equal to the work done by the expanding gases. So this much work is done by the expanding gases. So here reference, I can give reference to. Now I will discuss about facts about heat. So what are the facts which sometimes we have the confusion? That confusion has to be sorted out. Energy that flows from something warm, is hot, to the something cooler. So what is the heat? Heat will always in the transient, I told. It will always move from hot zone to the cooler zone. So that we have to understand. A hotter substance gives kinetic energy to cooler one. So this is a transfer of the kinetic energy. Hot will have more kinetic energy because molecules are moving very fast, and that is why it is having more heat or the more temperature, and it will move from hot to the cool side. Heat is the transfer of energy between two objects due to temperature difference. So heat is what? It is a transfer of energy between two objects due to temperature difference. Heat is measured in joules. because it is a form of energy. Heat and joules both are energy, and the heat both are having the same unit because both are energy. The name of the transfer process is heat. The name of transfer process, the heat is, this energy is inside, but when it is transferring, it is called the heat. What gets transferred is energy, and what is the transfer? That is called the energy. There is a circular nature to the definition used. Energy does work or produce heat. Energy does work, but energy is the combination of heat and the work. So energy is the combination of work and the or produces heat, but heat is a transfer of energy. But heat is a transfer of energy. Very, very important facts are here. We should take care of this type of concept. Temperatures. What is the temperature? Because heat will move from high temperature to low temperature. But what is the temperature? Temperature is the property which determines the direction heat will flow when two objects are brought into the contact. So if you see here that if two objects are there, this is the A and this is the B, and this is at 100 degrees centigrade and this is the 30 degrees centigrade. So what will happen? Temperature is the property which determines the direction of heat. So this Q will move from high temperature to low temperature. So this is called the temperature. Temperature is the property which determines the direction heat will flow when two objects are brought into the contact. So in my next topic, I am going to discuss one or two problems related to the work and heat. Then next classes, I will go for the first law of thermodynamics, which is the conservation of the mass. I am referring this book by Sengel, Thermodynamics and Engineering Approach, Tata McGraw-Hill's. Also today I have taken few topics from slideshareplayers.com, and any questions you are welcome to ask. My email ID is yddwivedi@gmail.com. I would like to thank for your great patience. Do like and ask the questions and subscribe this channel. Thank you very much for the joining my class. We will meet you again with some problem related to the heat and work. My next class, I will just discuss about the steam table.
Like, share and subscribe. Hit the bell icon for more updates.